Okay, so in this video we're going to talk about the ratio and root tests. Now, if we had had the ratio test, this would have made some earlier things that we've done easier. And in fact, some of the logic that goes into these tests kind of has been used already. So if you recall from my comparison test section, the last problem we did was like n factorial over n to the n. And basically, I used for my limit comparison n factorial over n plus 1 to the n, which to be honest isn't exactly the ratio test. I didn't actually do the ratio test to show that this converged, but I used some of the logic which was comparing it to the geometric series, and that's kind of what we do here in the ratio test. So basically the idea here is that in order to determine how quickly the terms of a series are decreasing or increasing is to calculate the ratios of consecutive terms. So for a geometric series, if you recall, we know that our common ratio is found by taking one term and then dividing it by the previous term. So if you think like 1, 2, 4, 8, if we took 4 and 2 and divided 4 by 2, you get 2. And if you took 2 divided by 1, you get 2. And if you take 8 divided by 4, you get 2. That 2 is our common ratio. So that's all this is saying, is that we take one term and divide it by its previous term. And if we take that absolute value and find some r here, this common ratio, as long as that r is less than 1, absolute value of r is less than 1, it converges. That was the concept of a geometric convergence. So basically, we use that same logic now to talk about our ratio test. And we go, all right, well, what if we took the limit as n approaches infinity of any kind of sequence we might have, a sub n plus 1 divided by a sub n, and if we could show that that is less than 1, then we know that, because it's this absolute value here, that this series would converge absolutely, which is a really strong statement. So if we could show absolute convergence, then we know the series converges, and we know it acts in a really predictable way. That is, we can rearrange to maybe show what the exact sum is or whatever. Now, that's basically what we're doing here, the ratio test and absolute convergence. So basically, if we can show that if we can find this limit as n approaches infinity to be less than 1, then we know that the series here will converge absolutely. And if it's greater than 1, then we know that it diverges. Or if it goes to infinity, it also diverges. I mean, infinity is greater than 1, I guess, technically, but yeah. So if it's greater than 1, or if it's equal to infinity, then it's divergent. So we know not to waste time trying to find the sum. And if it's equal to 1, though, so if we ever find something that equals 1, it's inconclusive. We don't know if it converges or diverges. We have to go somewhere else to show whether it converges or diverges. So we have to use a different test. So it doesn't work for everything, but there are times when it's quite handy. So let's take a look at an example. So determine whether this series is convergent or divergent. So basically what we're going to do is, first of all, I recognize that this is alternating. So maybe I'd use the alternating series test. But the problem here is that this n here over 5 to the n, if it was just like 1 over 5 to the n, easy enough. It would just be a geometric. If it was like, I guess, n over, I don't know, something else. Basically, this n is causing an issue. So the alternating series test isn't going to really work. Now, if we think about this, a sub n is negative 1 to the n times n over 5 to the n. And a sub n plus 1 is negative 1 to the n plus 1 times n plus 1 over 5 to the n plus 1. So that's what our a sub n plus 1 is. So basically what we're going to do is we're going to take the limit as n approaches infinity, and we're going to do the absolute value. And one of the great things about this ratio test is we take the absolute value, so alternating or not doesn't matter. So basically this portion of these just determines our signs. So really we don't really need them, but we're going to take a sub n plus 1 over a sub n. So for us, that's going to be the absolute value of, again, this doesn't matter in an absolute. So n plus 1 over 5 to the n plus 1. There we go. Absolute value. And we're dividing this by a sub n, which is here n over 5 to the n. So if we think about this thing, again, first of all, n here is 1 onwards, so we don't need this absolute value because 1 plus 1 is 2. It's positive only. This would only be positive, and these are only positive, so we're okay there. We don't actually need the absolute value, but it's equal to n plus 1 over 5 to the n. Now think about this one, 5 to the n plus 1. Anytime I see math in the exponent, I'm thinking, how else could I rewrite that? That would be 5 to the n times 5 to the 1. Because again, if we multiply two things same base, we add their exponents. Okay, so that's the top here times the bottom reciprocal. So we're going to do 5 to the n over n. And again, this is all limit as n approaches infinity. So we can cancel 5 to the n's here, and we get the limit as n approaches infinity of n plus 1 over 5n. Okay, now at the infinites, this is like saying only this power matters on top, n, and only this one matters, 5n, which is 1/5. So the limit as n approaches infinity of this thing is 1/5, which is less than 1, so it has absolute convergence. Boom, done. Easy enough. So that's all we need to show. Absolute convergence, it converges, we're good to go. So now we could always find the, estimate this infinite sum or whatever, or spend time trying to prove that it is a particular exact value if we want. All right, so let's take a look at another one. All right, we have another alternating series, but again, we have this like complex issue. We have 3 to the n over 2 to the n n cubed. So this is like a p series portion, but then these things here are geometric series. So it's kind of a geometric and a p series where basically it's 3 over 2 to the n 1 over n cubed. So like this geometric series would diverge, but this thing would converge. So multiplying them together, it's like, oh, I don't really know. And then we also have the fact that it's an alternating series. So that's kind of why we're really not going to use alternating series here, is because it's a kind of a complex function here. And also I have no clue how to integrate, so obviously we want to do the integral test. So we're going to try the ratio test. So we're going to take our a sub n here being 3 to the n. I'm just going to ignore this absolute, because if we think absolute value of a sub n, since we're taking the absolute value anyway, this alternating series doesn't really matter, since it's just going from positive to negative. That's our a sub n. And our a sub n plus 1 is going to just be 3 to the n plus 1 over 2 to the n plus 1 and n plus 1 to the third power. Okay, so we're going to jump into the limit. The limit as n approaches infinity of absolute value, 3 to the n plus 1 over 2 to the n plus 1 times n plus 1 to the third. And this is all divided by a sub n, which is 3 to the n over 2 to the n to the third. Okay, so again, I don't have the negatives here because they don't matter in an absolute value. So this would be 3 to the n times 3 over 2 to the n times 2 times n plus 1 cubed times our 2 to the n cubed over 3 to the n. So we're multiplying the reciprocal. Okay, now 3 to the n's are going to cancel and 2 to the n's are going to cancel, and we end up with the limit as n approaches infinity of 3n cubed. And because n is positive, I don't need this absolute value anymore. I can drop it over 2n plus 1 cubed. Now, if we think about this thing here, if I FOIL this out, basically I'll have a, so this is 3n cubed over, this would be like a 2n cubed times some other, or plus some other stuff, plus or minus some other stuff. But the highest power would be an n cubed. So at the infinites, the only thing that matters is this 3n cubed and 2n cubed. And you could multiply this out if you want to make sure, but I know how this multiplies out, at least for the first term. N cubed is what it would be. Okay, we'd have some n squareds, we'd have some n's, and we'd have a constant, but like 2 times n cubed is going to be 2n cubed, and it's the highest power, so I only have to worry about it. So at the infinites, these n cubes would drop off, and we get 3 over 2, which is greater than 1. So because it's greater than 1, it diverges. And since it diverges, we know not to waste time trying to find the infinite sum, because it diverges. Okay, now let's talk about that infinite sum. If we're going to estimate a sum, so if we're dealing with alternating series, then we use the methods we use in alternating series. Absolute value of r sub n is less than b sub n plus 1. However, if we're dealing with a positive series, then we use one of two methods. Basically, if r sub n is equal, which is equal to, so our ratio here is decreasing, is a decreasing sequence, okay, and r sub n plus 1 is less than 1, then r sub n is less than or equal to a sub n plus 1 over 1 minus r sub n plus 1. R sub n plus 1 would just mean we add 1 into here, which means we add 1 into this. So this would be like a sub n plus 2 and a sub n plus 1. That's all this is saying. Okay, so just as a note, what this r sub n plus 1 is equal to a sub n plus 2 over a sub n plus 1. That's all that is. Okay, and if our ratio here is an increasing sequence, then r sub n is less than or equal to a sub n plus 1 over 1 minus l. Okay, where our L, if we go back here, L was this value in our, like, what is it equal to, the limit, okay, as n approaches infinity. Okay, so that's what this thing here, again, this is just our limit as n approaches infinity of a sub n plus 1 over a sub n. That's what that equaled. All right, so we need to see whether or not these are like increasing or decreasing sequences, but otherwise, then we just kind of plug it into this formula and see. Okay, so let's talk about determine whether this series is convergent or divergent. If it converges, use the 10th partial sum to approximate and find the error. So here we have 1 over n factorial. Now, n factorial is a definite candidate for dealing with by using our ratio test. The reason for this is because essentially we're going to end up doing some division here, and that's actually really good with factorials because as is, this goes off into like to 0, because as n approaches infinity, this would go to 0. So it kind of converges, but the problem is that like 1 over n factorial is definitely less than like or equal to 1 over n. But the problem is this is divergent. So it doesn't really tell us anything about whether this converges. Because it's a p-series with a power of 1. And if we have like 1 over 2 squared, then like 1 over 1, so when n is 1, that would be 1 over 1, 1 over 1. That's okay. It's equal to it. But when we go on the second term, 1 over 2 factorial is 2. And 1 over 2 squared is 4. So 1/2 is definitely not less than or equal to 1 over n squared. So this isn't really going to work for us using direct comparison. So we're going to jump into our ratio. And one of the nice things about this is that, like I said, because this factorial, we really do want division. Because if you think about it, let's start with like 3 factorial over, say, 4 factorial, okay? 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And if you notice, that is like saying 3 factorial over 4 times 3 factorial. And so factorials tend to cancel out, at least at some stage. If you have one over the other, they will be the same at some point. And so then we can kind of use that information to cancel them. So we're going to use that same concept here. So a sub n is 1 over n factorial. A sub n plus 1 then is 1 over n plus 1 factorial. So the limit as n approaches infinity of, we don't really need the absolute value here because factorials here are going to be positive anyway, but 1 over n plus 1 factorial divided by 1 over n factorial. So like I said, I'm going to drop this absolute value now. We end up with the limit as n approaches infinity of our n factorial over n plus 1 factorial. because, again, multiplying by the reciprocal, we put this n factorial on top. So we're here. Now, at infinity, we have an infinity over infinity. And I don't know off the top of my head any method to take the derivative of n factorial. So that's out for Hopital's rule or something like that. But if we notice, think about what n plus 1 factorial is. That's like saying n plus 1 times n minus 1 times n minus 2, etc. And this would be n times n minus 1 times n minus 2, etc. So that is to say, this is n plus 1 times n factorial, and this is n factorial. So these cancel, and we get the limit as n approaches infinity of 1 over n plus 1, which is just going to be 1 over infinity, which is 0. So that's less than 1, so it is absolute convergence there. Okay, so we know it converges. Now we can find the sum. So let's start with the 10th partial sum. The 10th partial sum would be from n equals 1 to 10 of 1 over n factorial. So we'll go over to Desmos for this. Sum, so we'll go to functions, 1 to 10 of 1 over n factorial, and we get 1 plus 71828180115. So that's our approximation. But now we need to determine, hey, how is this actually how close is this? So we're going to make sure we check our error. So first of all, as a reminder, if we look back here, if it's a decreasing sequence or increasing sequence, we use different things. And alternating, we use our alternating series test. So this is not alternating. And what we're looking for is if our ratio is decreasing or increasing as a sequence. So we need to think about our ratio. Right here, this is our ratio, this thing. Okay, our simplified ratio here, r sub n, is 1 over n plus 1. That is what our r sub n is. It's a sub n plus 1 over a sub n. Okay, so that means we have 1 over n plus 1. So if we think about this in terms of, at the first term, the second, and so on, when n is 1, this would be 1/2. When n is 2, this would be 1/3. 1/4, 1/5, etc. So this is a decreasing sequence. So because it's decreasing, we are going to use this formula for our remainder. Okay, so if we go here, we'll just take a look over here. Okay, so I just want to paste it in so we have it as reference. Okay, so basically, our remainder, r sub 10, is going to be less than or equal to a sub 10 plus 1, which would be a sub 11, over 1 minus r sub 10 plus 1, which is also 11. Okay, so a sub 11 would just be, since a sub n is 1 over n factorial, a sub 11 is just 1 over 11 factorial. And since r sub n is 1 over n plus 1, r sub 10, okay, r sub 10 plus 1, that's going to be r sub 11, which is going to be 1 over 11 plus 1, which is 1 over 12. So we plug this into our formula. R sub 10 is less than or equal to a sub 11, which was, again, 1 over 11 factorial. 11, all these ones next to my factorial. That is an 11. This is a exclamation mark. Okay. And it's over our 1 minus r sub 11, which is 1/12. Okay, so if we check this out, we'll see how good our estimate is. 1 over 11 factorial. There we go. Over 1 minus 1/12. And we get our error rate. And if you notice, that's a pretty darn good error rate. Our r sub 10 is less than or equal to 2.296443267 times 10 to the negative 8. So moving this decimal place over 8 times. So this is actually very close to our actual sum. So that is how we check for estimate error and things like that. Okay. So anyway, now let's move on to the root test. Now, if the limit, so it's very similar to our ratio test as far as the same kind of things that we end up with. But basically, if we have some sequence here, or some series, we take the absolute value of it, and we take the nth root of it. And if the limit as n approaches infinity of that is L, which is less than 1, then this series is absolutely convergent, just like our ratio. And if that same nth root leads to an L greater than 1 or equal to infinity, then the series is divergent, just like our ratio test. And if we get 1, then our root test is inconclusive. So we're using the same basic concept as before, where our L here being less than 1 converges, greater than 1 diverges, equal to 1 inconclusive. Now, when do we use this root test? Well, we use it when we have something to some power of n. So, if we take a look here, determine whether this series is convergent or divergent. So if we look here, this whole thing is being raised to the n. So all we have to do, it's really actually great for this. Like if we see something in this form, oh yeah, the root test is the way to go. So what we do is we just take the nth root of this absolute value of n squared plus 1 over 2n squared plus 1. Granted, these are already positive, so it doesn't really matter. And these are all squared here, top and bottom, or not squared, sorry, to the nth power here. So I'll just combine that to the nth power. We're taking the absolute value. Okay, so I don't really need the absolute value sign here, but we need it for the nth root just in case, you know, it's even. So you have that absolute value. And the nice thing too is by turning into the absolute value, we get absolute convergence, which again is a stronger statement. So nth root and nth power cancel. And we're taking this as the limit as n approaches infinity. So that means that the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1, well, that's just going to be, because of infinity, 1 is basically holds no bearing on this top, so it's n squared over 2n squared, which is 1 over 2, which is less than 1, so this converges absolutely. Absolute convergence here. Okay, so let's take a look at another one. Determine whether this series is convergent or divergent. Okay, so here we have n squared, but the big thing is I have an n in the exponent for this whole thing. So I'm going to use the nth root. Nth root, so we're doing the root test, limit as n approaches infinity of the nth root of 1 plus 1 over n to the n squared. Now, if you are wondering, how's the nth root applied to this nth squared? Well, we have to think about what is the nth root. That's like saying 1 plus 1 over n to the n squared, all being taken to the 1 over n. 1 over n. So if we have an exponent to an exponent, that means we multiply those exponents. So we get n squared over n, which is just going to be an n. So we end up with 1 plus 1 over n to the n. And this is the limit as n approaches infinity. And you may think, oh no, we still have that n. Well, that's not really a big deal, because you may recognize this as we take this thing to infinity. That's e. E is greater than 1. So this diverges. Okay, so again, this is just one of those ones. This goes to e. And if you don't trust it, graph it. 1 plus 1 over x to the x. That has some horizontal asymptote, y equals e, and it's e. That's the definition of e right here. Okay, let's take a look at another one. Determine whether this series is convergent or divergent. Okay, so first of all, we have an alternating series. So that's what we use this absolute value for, realistically speaking, is for to deal with that. So essentially, we're going to take the absolute value. That would lead us to 1 over ln of n to the n. Okay, which really means that this is 1 over ln n all to the n here. So we already took the absolute value. Oops. All right, let's bring those back. Okay. And we're going to take the limit as n approaches infinity of the nth root of this thing here. This leads to canceling, and we get the limit as n approaches infinity of 1 over ln n. That would, and again, it starts at 2 because ln of 1 is undefined, or is 0. Okay. And so, and then that would cause this to be undefined. So we're starting at 2. But as this goes to infinity, natural log of infinity is infinity. So it's 1 over infinity, which is 0, which is less than 1. So it converges absolutely. So that is the root test. And as you notice, it's pretty simple. So essentially, we have the ratio and root tests. And they follow pretty much the same rules. It just depends on when we need to use them. Thanks for watching.